Students, so in today's class we are going to look at the third application of the Gauss's theorem. The first one which we saw was infinitely long straight uniformly charged wire, and the second one was infinitely uniformly charged plane shell. Okay, so this is the third application, that is uniformly charged spherical shell. So in this case, we are going to consider a thin spherical shell of radius, for example, r, okay, and which has a surface charge density sigma. Let's consider a positive surface charge density, so which is sigma greater than 0. Okay, so let's first draw this spherical shell. Okay, so let us consider this is my spherical shell. Okay, this is positively charged, sigma is greater than 0, that is surface charge density is greater than 0. Okay, so let's consider this is plus sigma. Okay, so let's say center of this shell is O and the radius of this shell let's consider as r. Okay, now we are going to find out the electric field due to the spherical shell, uniformly charged spherical shell, at a point outside the shell, at a point on the shell, on the surface of the shell, and at a point inside the shell. So we are going to see three different cases wherein first we are going to find out the electric field due to this uniformly charged spherical shell, number one, outside the shell, on the surface of the shell, and inside the shell. Okay, so let's consider the first case that is outside the shell. Okay, so let me consider a point P outside the shell. So let's consider this is my point P over here, which is outside the shell. Okay, so now let this point P be the observation point, and let's say this point P is at a distance of r. Let's consider small r. Okay, and this r, which is small r, is greater than the capital R, that is the radius of the shell. That means that your point P, that is the observation point, is lying outside the spherical shell. Okay, we need to calculate the electric field at this particular point. Let's say that electric field is E of r. Okay, so we are going to calculate the electric field at point P, that is at a distance of r. Okay, that is our intention. So from the symmetry of the problem, the Gaussian surface in this case is going to be obviously a concentric sphere, because this is spherical shell, right? This is like a ball, okay, on which the positive charge is present. So the Gaussian surface always passes through the point of observation, the observation point. So obviously the Gaussian surface in this case is going to be a bigger sphere, okay, bigger than this one. Okay, so it can be called as a concentric sphere of radius smaller. Okay, so let us draw that Gaussian surface now. Okay, so this becomes this dotted concentric circle which you see, that is considered that as a Gaussian surface, that is a concentric sphere. Okay, so now since this is a positive charge, the electric field will be obviously pointing radially outwards here. Okay, and if I want to consider the area vector is again taken perpendicular to the surface outwards. So let's draw that area vector also here. So let's say ds is the area vector. So if you see, electric field and area vector are in the same direction. Okay, so now as usual, let us apply the Gauss law. So by Gauss theorem, okay, what we can say, the closed line integral of E dot ds, that is basically what? It is the flux, the total flux coming out from this Gaussian surface is the total charge enclosed in the Gaussian surface divided by epsilon naught. This is our equation 1. This we obtain from the Gauss law. Okay, so now the contribution to the total flux from the entire spherical Gaussian surface of area, what will be the area of the Gaussian surface? It will be 4 pi r square, correct? The area of the sphere. Okay, so the total contribution of the flux, that is this part, the total flux coming out from this Gaussian surface will be how much? Therefore, let's write that down. So the flux, that is E dot ds, correct? This is nothing but a flux. Okay, I'm just putting it over here for understanding. Okay, this is nothing but a total flux coming out of this Gaussian surface. That is going to be electric field we have taken as E, so let's put it as E only. Okay, and the area of the spherical surface, that is the Gaussian spherical surface, will be what? 4 pi small r square, correct? The radius of this Gaussian surface is small r, so it is going to be small r square. So let us call this equation as 2 over here. Okay, now let us write down the equation for the charge. Okay, so let us consider the surface charge density. So surface charge density that is sigma, okay, will be what? The total charge enclosed inside this Gaussian surface that we have considered as Q divided by the total surface area. Correct? The total surface area. So what is going to be the total surface area over here? The total surface area is going to be 4 pi capital R square. That is capital R. Why capital R? Because it will be the radius of this spherical shell. Because we are finding the surface charge density for this shell. Correct? We are finding the surface charge density for the shell. So we will be considering the area of the shell. So this is the difference we have to note over here. Okay? Because while finding the flux, we find out the flux through a Gaussian surface. Okay? So we will be taking radius as small r. That is the radius of the Gaussian surface here. Okay? But when we write for the surface charge density, we take the surface charge density of the spherical shell. So what is the radius of spherical shell? It is capital R. So you will be putting capital R over here. Okay? So that is the difference. So let us call. So from here, what will be your Q? So Q is going to be sigma multiplied by 4 pi capital R square. So let us call this equation 3. Okay? So now let us substitute equation 2 and 3 in equation 1. So substituting equation 2 and 3 in 1. What we have got this flux as E into 4 pi small r square. Substitute it over here is equal to Q we have obtained as sigma into 4 pi capital R square upon epsilon naught. Okay. So what is going to happen over here? 4 pi will get cancelled. Okay. So E will be equal to sigma upon epsilon naught capital R square upon small r square. So this is going to be your expression for the electric field. Okay, at a point outside the spherical shell, like this, at a point outside the spherical shell. Okay, there is one more form you can write over here. So if you just substitute for your flux, okay, and keep your Q as it is, you get another form. So let's substitute only 2 in 1. Okay, we won't substitute 3. So substituting only 2 in 1, so you'll get, in place of flux, I'll put E into 4 pi r square. So you'll get E into 4 pi small r square, which will be equal to Q upon epsilon naught. So E will be equal to what? I'll just rearrange the terms. 1 upon 4 pi I'll take down. Epsilon naught is already there here. Okay, here. So 1 upon 4 pi I'll take down. Epsilon naught is already there over here. Q divided by this small r square. So if you remember, this is a familiar formula, right? This is the formula we had seen when we were discussing the definition of electric field. That is, electric field is 1 upon 4 pi epsilon naught. The source charge. The source charge is what over here? Q is the source charge divided by the distance square. That is the distance to the observation point from here to here, r square. So this is the formula we have already seen. So through this derivation also we can show the same thing. Okay, so these are the two formulae which gives you the expression for electric field at a point outside the spherical shell. In the next case, what we are going to do is we are going to consider this point on the surface of the shell. Okay, so let's consider the second case now. Okay, so in the second case, we have field at a point on the surface of the shell. So the observation point which was here at a distance of r, correct? P was here at a distance of r, is now brought over here. So this becomes P. Okay, now here what will happen? In short, that r becomes small r, which was here, right? Small r becomes equal to capital R, correct? Small r becomes equal to capital R because the distance to the observation point was small r that I made to the radius of the shell. So it became equal to capital R. So let's take the equation which we have already got. E is equal to sigma upon epsilon naught capital R square upon small r square. This is the expression for electric field at a distance of r outside the shell, correct? So now in this case, this is a special case, right, wherein we got small r equal to capital R. So let's substitute over here. So this will be sigma upon epsilon naught. In place of small r, or in place of capital R, I'll put small r. So r square upon r square will get cancelled. So E will be equal to sigma upon epsilon naught. Okay, this is the expression for electric field on the surface of the spherical shell. Okay, and now coming to the third case, that is field inside the shell. This is the third case, that is field inside the shell. So in this case, what is going to happen is, in this case, Gaussian surface will be a sphere of radius small r, correct, which will be smaller than this capital R. Okay, I'll draw the figure for you. Supposing this is my spherical shell. Okay, just excuse my drawing skills. Okay, let's consider this is my spherical shell. I'm just roughly doing it. Okay, and I have to have this point, observation point, now inside the shell. So my point P is inside the shell. Okay, so my Gaussian surface has to be passing through the observation point. So this is going to be my Gaussian surface, which is of the radius small r, and this is of the radius capital R. So if you see, small r is lesser than capital R over here. That is, the distance to the observation point becomes smaller than the distance to the spherical shell. Okay, small r is smaller than the capital R. Okay, so let's find out the flux over here. So the total flux E dot ds will be what? The electric field multiplied by the area of the Gaussian surface. So what is the area of Gaussian surface? 4 pi r square, small r square, because the radius of Gaussian surface is small r square. I'm finding the flux. Okay, so now let's apply the Gaussian theorem. So by Gauss law, okay, the total flux enclosed by the Gaussian surface is the total charge enclosed inside the Gaussian surface divided by epsilon naught. Correct? This we got as E into 4 pi r square. I'm just substituting this over here. Okay, but what is the total charge enclosed inside the Gaussian surface? Is there any charge present inside the Gaussian surface? No. The total charge is present outside the Gaussian surface, which will not be counted. Correct? The only charge which is present inside the Gaussian surface is always counted. Correct? But there is no charge inside the Gaussian surface. That is, Q is equal to 0 in this case. So this entire term will go to 0 once you substitute this Q is equal to 0. And therefore, E will be equal to 0 for the point inside the surface. That is, the electric field for any point considered inside the spherical shell, okay, will be 0. Okay, so this is the conclusion. So what are the formulae which we got? Okay, for outside the shell, the electric field at a point outside the shell is given by 1 upon 4 pi epsilon naught Q upon r square, or sigma upon epsilon naught capital R square upon small r square. Okay, for a point on the surface of the shell, we got an electric field formula as sigma upon epsilon naught, and for inside the shell, electric field is always 0. Okay. So now this property, that is electric field inside any conductor, is 0. Okay, inside electric field inside the shell vanishes. This property is called as the electrostatic shielding. Okay, it is called as electrostatic shielding, which we are going to come across again in our second chapter. Okay, what is electrostatic shielding? That is, the electric field inside the core of the conductor is always 0. Okay, this is called electrostatic shielding. Okay, now let us come to the graphical representation of electric field of a spherical shell. Okay, so let us look at the graphical representation of electric field of a spherical shell. So I'm going to plot E versus R. Okay, so now on this side we will represent when R is lesser than capital R, that is, the point is inside the spherical shell. Okay, at the center will represent R is equal to R, that is basically on the surface of the spherical shell, and this side will represent R is greater than capital R, that is, the point is outside the spherical shell. Okay, so now inside the spherical shell we know electric field is 0. So basically your line will come something like this. Okay, till here. So electric field is 0 inside the spherical shell. At R becomes equal to capital R, your electric field on the surface, that is, the electric field on the at a point on the surface, we saw expression is sigma upon epsilon naught, that is the maximum value. Okay, so at the surface the electric field will be maximum. Okay, that is when R is equal to capital R. Okay, and then when you start going away from the surface point, you go away and away from the surface point, you are dividing it by R. Correct, you are dividing it by the distance. So your value of electric field as you go away from the surface will go on dropping and dropping. Okay, so as R becomes greater than capital R. As you go away from the spherical surface or spherical shell, your value of electric field will go on dropping. So this is the graphical representation of the electric field of a spherical shell. Okay, a single formula can explain you this, that is E is equal to 1 upon 4 pi epsilon naught Q upon R square. As you go away from the spherical shell, as R increases, your E will go on dropping. Okay, yes, so this is your graphical representation. Now few things you need to remember over here. The first very important thing is electric charges always reside on the surface of the conductor, and hence charged conductor behaves as a shell of a charge. Okay, there are no charges inside the core. Second thing, Gaussian surface always passes through the observation point. Okay, wherever you take observation point, your Gaussian surface has to pass through that observation point, see P over here. Okay, or in this case the Gaussian surface has to pass through the observation point. Third point you need to remember here is maximum value of electric field is at the surface of the charged shell. Okay, inside it is 0, on the surface it is maximum, and then it will go on dropping as you go away from the shell. Fourth point, electric field inside the conductor is 0 and is independent of the shape of the conductor. And the fifth important point is electric field on surface of the conductor is directly proportional to the surface charge density. Okay, so if you see this formula for the surface, for the point on the surface, E is directly proportional to sigma. As sigma increases, E will increase. As sigma decreases, E will decrease. So these are some few points you need to remember. So this was the last topic under your chapter 1, and the theory part. Okay, and we have come to an end of chapter 1. Okay, from next class onwards we will be seeing the chapter 2. Okay, so this is it for today. I'll see you in the next class with the next chapter.